going to have 7 groups of people. No one said put your hands down. So we're going to have you count off. We want 7 teams. And we do not want them to all be from one discipline. In fact, we want them to be mixed up. So the seismologists count off by 7.
1, 2, 3, 4, 5, 6, 7, 10.
No, that counts right over. 1.
1,
2, 3, 4, 5, 6, 7, and 1. Okay, now the non-seismologists, raise your hands.
1,
2, 3,
4,
5,
6,
7.
No, 1. 1, 2,
4,
5,
6, 7,
1, 2,
3,
4, 5.
Okay, so if you're a 1, that's one group. If you're a 2, that's one group, and so on.
So you're saying we needed to remember the numbers?
Yes.
This is part of the exercise, yes. So Onno has 7 sticks.
I have 7 sticks that I'm going to distribute in a few minutes before I'm going to give a few explanations. You will have a job to do within these groups. 5 people in each group. And with Alan, we decided to give you more time than just this tutorial today. So the rules of the game are that you analyze the data and present the results of your group on Friday?
On Friday at the end of the day.
On Friday at the end of the day. And that's all you need to know. On the stick, you'll have lots of information that will provide you the background that I want you to know. It doesn't provide you everything. The missing part is what we want you to do with the work of your group. Now, what this all is about, I'm going to show you a few slides. Remember, the basic story I was talking about this morning is mass flux. So I'm just coming back to this view graph that I showed this morning that provides a little of the background. This wedge theory issue that showed that any orogenic wedge will grow in a self-similar manner, simply governed by the fact that its mechanical properties, if they remain stable over time, will determine its shape. Now, this simplistic view becomes more complex if you are dealing with materials that are not ideal Coulomb materials. Natural rocks are not. They tend to behave a little more complex, so the wedges do not, the real world wedges do not show this kind of isotropic structure, but they are showing faults, strain localization, folds, and all this kind of family of tectonic structures and complex kinematic evolution that nature does as well. Before jumping to the next examples, however, remember that I also introduced this view graph here that shows the behavior of these wedge systems in alpha-beta space. Alpha being the surface slope, beta being the angle of subduction or the dip angle of the master fault system. And you'll remember that I was alluding to the fact that any system that is stable within this framework will plot along these lines and will be critical. Critical meaning that it is at the verge of failure throughout and is sliding over its base without deforming. Now, as soon as you are perturbing it, it will start to deform. Perturbation will mean that it will also change either its dip angle or its surface slope. So if it drops into this space down here, it will start reacting by contractional deformation. If it moves into the blue area, it will become totally stable. It will simply not do anything. It will just slide over its base. It will be mechanically stable. if it moves across the upper critical limit into this upper boundary, it will fail by extensional deformation. So in fact, the kind of kinematics that we see in the real world find their representation in this simple view graph. That may be one of the things that might help you interpreting the data that you will be seeing. What will you be seeing? On the USB sticks that I'm going to distribute in a minute, I have a large series of movies from experiments. I would have loved to have you do the experiments, but it's time consuming and I had some luggage limitations. I couldn't bring along 12 sandboxes for you to work with. As I mentioned, if we get a chance of getting to the beach, I don't know if this is planned, we might do some real experiments in the sand. So anyway, the kind of experiments that you will be seeing movies from, this is what they're usually showing. This is the kind of shear box that we are using, usually set up with an electronic stepping motor or a similar system that is driving a conveyor belt below the system, dragging the material. It uses material, it may use material like sand. It was mentioned before by Dave that these granular materials are materials that exhibit similar properties as natural rocks. I'm just showing here on a strength strain diagram the typical pattern that natural rocks undergo with an early stage of elastic deformation, some unelastic deformation prior to failure near the peak strength, and a drop in strength to a steady state frictional strength that is a bit lower than the peak strength. This is, by the way, an important property because it allows rocks to localize deformation. If this didn't occur, rocks would have a much bigger problem of localizing deformation in the brittle field. And the yellow here shows sand and other granular materials that we have, so they virtually show the same kind of behavior. This is important because it relates to the issue of proper dynamic and kinematic scaling of the experimental materials. If this would not occur, we would have a problem relating these observations to nature. So the key issue is to tune your material such that the ratio of normal stresses to shear stresses within the entire experiments is the same as in nature. Okay, the movies that you will be seeing are monitored by a system of digital cameras, and there is not just the conventional kind of optical imagery that you may be aware of. We use a technique that is called particle imaging velocimetry. That is a bit more complex. This is all the scaling issue. I'm not going to go into detail there. You will be finding all this material on the stick. The particle imaging velocimetry that we use to explore these systems tracks the detailed internal structure of the entire experiment and calculates the complete particle displacement field. And it does so by moving an interrogation window across the granular structure that our experiment has. And from one time step to the next, it identifies patterns. It identifies similar identical patterns, and it uses these to calculate the particle displacement field. And if you have the complete particle displacement field, what you can do, you can calculate the complete strain tensor, and you can then decompose the strain tensor for all the components that you're interested in. So this is basically what we do, and it allows you to produce nice images like these. This is, for example, showing an experiment where the rotational shear has been extracted. That is a wonderful property to illustrate the faults that are active in any one time increment. Or down here, we extract the flow lines, which shows you the kind of particle trajectory within such an orogenic system. In the series that will be distributed to you, you will have a range of movies from different kinds of experiments, and I want you to explore them with a series of questions Some of these you will find on the README, that's on the USB stick. Others I want you to think about yourself. You are from various fields, you will have different kinds of questions, different kinds of aspects that you will possibly be interested in when you see these movies. Take them and do with them whatever you want. We are really curious in what you will be showing us on Friday, what has emerged from the analysis that you've been doing. Just as a look at what we can also do, we can also scale these experiments to produce earthquakes and earthquake cycles with the proper granular materials. This will not be the topic of the present session, but you can do all kinds of such experiments if you tune your materials such that they do not just scale for the forces that I've been showing you, but also scale for elastic properties, for velocity dependence of frictional strength and so forth, which is what you need to do if you want to do earthquakes. This is just showing one example where you can see the particle displacement field for a propagating seismic rupture, showing the complete particle displacement field. This was here for a single rupture, but you can really look at the entire evolution to see how does rupture evolution, any one of these jumps is a seismic rupture, and evolution of topography and permanent deformation in the upper plate correlate, produce synthetic earthquake cycles, do all kinds of things. So this use with the high resolution imaging technology is a wonderful tool to really explore how deformation in the brittle field is accumulated and how it integrates over various timescales. So that's just a little look into the future. I'm now going to distribute these movies. You will all have all movies, so you will also be able to see what the others are doing. But in the README that you have, each group is assigned a certain number of movies. It's between 2 and 4 movies, and I want you to analyze these in detail with whatever you think of. Some of the questions, as I said, are on the README. I would like you to address these, but possibly also other questions that you want to think of that maybe I have never thought about. So this is one of the parts where I'm really curious what emerges from the perspectives you have. I will be happy to answer any kind of questions. Each of these group assignments is headed by a certain theme. I'm not giving it. You'll find out. You'll find out. What?
That's what we'll ask them on Friday.
Exactly. I want to know what kind of theme you have been seeing, really, and what you have been able to retrieve from analyzing the movies. It might be helpful for identifying the theme by also looking at the movies of the others. It will be important to try to analyze quantitatively as much as you can with the simple means that you have. You don't have the means that we have in the lab when we explore these movies, but you can do some quantitative or semi-quantitative evaluation of the mass fluxes and the kinematic response of the system to masses being fluxed around. Remember, this might help us to provide an intuitive approach to what nature may be doing as well in the brittle field. All the experiments that you have are experiments relating to the brittle field. We are not exploring viscous deeper crust and upper mantle business. This is a highly interesting topic in itself, but it would add too much complexity to be dealt with in a short exercise in the time that you have. Any questions at this point? Okay, so
we have rooms you can look at upstairs on the 4th floor and the 5th floor. So why don't we have groups 1 through 5 go upstairs and groups 6 and 7 stay here? What do the professors do? The professors...
You're encouraged to do the same. I have one more stick here. And on Friday we can see who is cleverer.
So all the ones come up here. All the ones come here and get your stick.
Get your stick, and on the README, look at the movies assigned to group 1. And the same for the next groups. So here, that's 1.
So this is for team captain. You're 1.
All the ones, follow her. And group 2.
Who is all the group 2s? Group 3?
Group 3? Yeah, it's 1 per group.